we measure a rate of a reaction? Well, if we do have a plot, if we have some way to know the amount in either moles or in molarity, meaning moles per given amount of volume of space, right? If we have a way to, measure what the concentration is versus time, then what we call this progress curve, which changes, right? The concentration changes as time proceeds. And now look at this reactant. HI is the reactant there. You can see that the reaction rate at which it disappears is related to, or is indicated by, is defined by the slope of this line. The slope of this line. And you can see that the slope of this line, let me draw it here on a regular piece of paper. So if I look at, for what I'm going to draw here, the concentration of A versus time, if A disappears time like this, then what we see is that, so if this is 1 molar, 1 mole, right? It's the molarity, because we're going to be in some fixed volume where this given chemical reaction occurs, the molarity and the moles will be the same because the volume is fixed, right? I mean, they won't have the exact same number, but the curvature, the shape of this graph, whether you're talking about moles or molarity, will look the same versus time. So if I look at this and I say I start off with 1 mole, I let time proceed this much, and then I find out my new concentration, right? The slope between those 2 points can be used to define the definition, define the rate at which the chemical is being removed, right? So if I went down from 1 to 0.9, right, then I've lost 0.1 moles, and if that happened in 1 minute, then I can say the rate of disappearance of A is 0.1 moles per minute, or 0.1 molar per minute, right? So that is how we identify the rate at which things are either lost, or if we're monitoring C, right, the progress curve would look like this, right? C's concentration versus time. Now, when we're talking about concentration, we have a way to kind of quickly identify that we're telling people that we're talking about concentration. We write these brackets. Those brackets allow us to say, I'm talking about the concentration of C versus time. Okay? And then the slope of that line tells us the concentration. Here is the slope of a different chemical reaction. Let's say this is chemical E going to G, and this is the amount of E versus time. And let's say this slope of this line is linear, meaning the rate at which it's disappearing is the same at the beginning of the reaction, the slope here, compared to the slope at the end of the reaction. The slope is not changing, it's the same all the way down. Right? But this slope here, which I've drawn, where A reacts with B to form C, at the beginning of the reaction, the rate was whatever that slope is. But now, down here towards the middle of the reaction, the slope here is much shallower, much slower. Right? Now let's see. Camille, what do you think? What are our units for this slope? I mean, I kind of already said it, but we want to make sure we can identify what the units for this slope are.
Mole.
Mole
Per minute.
per minute. Very good. And it's right over here. But just like any old equation on a graph, it's rise, the y-axis units, over run, divided by the x-axis units, right? So those are our units. And we see that the moles per minute that are lost for A decreases as I proceed in this chemical reaction. Why do you think that happens, Camille? Why do you think that for this chemical reaction and, many chemical reactions, the rate at which A disappears slows over time? Why do you think that would be?
Well, is it because there's a loss in energy?
Well, let's look back at this little super fun video here. Let's watch this super fun video and watch the rate at which A and B disappear. Okay? So A and B initially disappear fast, but then it starts to slow how fast it disappears. Why is it that it's slowing?
So you're lowering the amount of the reactant.
That's right, because as the reaction occurs, you're changing the concentration of A and B that you have. So that's the case, right? When a reaction occurs, as a reaction occurs, right, if it's A and B that need to actually collide to form C, as the reaction occurs, the concentration of A will decrease fast, but then it changes, right? The rate at which A disappears changes versus time because the concentration of A gets smaller and smaller and smaller, and the concentration of B is decreasing as well, and so it's harder and harder for those A and those reactants to find each other in the vessel. All right? Okay, very good. So we have the ability to then look at a curve like this and find the slope or the rate at which the reaction is disappearing, the reactant is disappearing, or that the product is appearing. So here's another example. Here's NO2. See, it's in brackets. Do you remember what those brackets mean, Sarah? What did I say those brackets mean when they're around NO2 like that?
Yeah, that is the concentration.
That's right. So those brackets mean we're looking at the concentration of NO2. And Sarah, does it look like this reaction rate decreases over time or stays constant over time? Does this reaction rate decrease over time or is it staying constant over time?
Yeah, it looks like it decreases over time.
How can you tell?
The slope just gets a little bit flatter.
That's right.
It's not the same.
That's right. Very good. The slope here gets shallower, and you can look at the red without the blue, and you can see that it's a curve, right? It's not a completely straight linear relationship. So because of that, we have to have different ways of talking about the rate of a reaction, and you won't really be probed too much on this, but there's what we call the initial rate, which is, ta-da, the rate at the initial point of the reaction, the beginning. Instantaneous rate means the rate at a given point, right? So if I want to know what the rate is right at 200 seconds, for example, then I need to find the rate of that point. Now, finding the rate of a point is what you call taking the derivative of a curve, right? So that's not something as straightforward as taking 2 points and finding the slope of that line, right? But we'll show some examples of that later on. So we have the initial rate, the instantaneous rate, all right? And then if we talk about the average rate over a given time period, we're just talking about using those time periods, those time points, to find what the resulting rate is. Okay? So for this question, what's the average rate for the disappearance of B between 10 and 40 seconds. Okay? We would like to be able to calculate the rate of the disappearance of B between 10 and 40 seconds, average rate. All right, so I'm going to break you guys up. We got 3 people. I'm going to break you guys up into 2 different groups and give you guys the opportunity to try and answer this question. All right, I'll come by and visit the groups, so you guys try to work together until I get to your group. All right. Let's see, Alyssa. Did you get an answer for this one?
Yes, sir.
Did you guys get to work on it together, or did that not work, that breakout room?
It worked for us.
All right, great. What did you guys decide on?
We decided on A.
A as in apple?
Yes, sir.
Let's see if that's right or not. Oh, it was B. Oh,
Oh, we tried so hard with it.
Wait, how is it positive if the slope is going down?
we'll talk about that. What's funny though, is our group, I was in our group and we got 0.02. I didn't do the math, but I was just kind of following along. So we missed it in our group. Let's see what we did wrong. And then we'll talk about why the positive and negative and what that business is. Okay, so what did you do to do this one, Alyssa?
So it sounds like the average rise over run for that problem. So from 10 to 40 is about 30 seconds. And then the problem starts concentration-wise at about 0.2, and it goes to about 0.02, I guess.
Oh, you went down to 0.02? Is that where you went?
Oh, we just approximated, so,
Yeah, it should
and
be.
then rounded at the end.
Okay. So, 0.2 minus, 0.02. So we got 0.18. That's changing, that's rise, change in Y, right? Over our change in seconds divided by 30. Okay. That looks good. Okay. Very good. Now, the positive negative thing, right? If they had just said what's the most likely the rate, or what is the rate of change, then it would be the negative. But because here they said the rate of disappearance, they're basically already saying that it's a positive value, or sorry, that it's a negative value. So how fast is that negative value? Negative 0.006. So they want to test you on that sort of thing, but kind of like the delta H business before, negative and positive, right? We want to be able to recognize that when we see negative, that means, we want to recognize the intricacies here. You won't be tested on it again, but we want to see that when they're talking about the disappearance of something, then they're already saying that it's going down. How fast is it going down would be a positive number then. If they're just talking about the change, then you can indicate whether it's going down or up with that positive or negative value. All right, so Sarah and Jace, did that make sense? What did we do wrong?
We just did 0.4. It was just a simple mistake. I think we just overlooked, because we're at 10, we just set it equal to 0.4 instead of 0.2.
Okay.
So.
Okay. All right. Excellent. Okay. Then, as we mentioned, these reaction rates, the rate at which things change, is stoichiometrically related to the rate of either disappearance or appearance of our other reactants or products. So the rate at which A disappears will relate directly to the rate at which B disappears and directly to the rate at which D disappears by the stoichiometry little a, little b, little d. So we should be able to answer this type of a question. Here's a reaction. 2 A's combined with 3 B's to form 5 D's. And we measured the rate of disappearance of substance A to be 3.5 times 10 to the minus 5 molar per second. What's the rate of appearance of D? Let's see, Jace, do you think you can handle this one?
Yeah, the reaction.
How are we going to solve this problem? What are we going to do?
We're just going to do 5 divided by 2 and then multiply it by the disappearance of A.
Okay, so we want to know the molar per second of the rate of appearance of D, right? Molar per second of D. And we know that the molar per second of A is 3.5 times 10 to the minus 5. Molar of A per second, right? And then we just want to be able to relate the molar of A, moles of A, to moles of D. And that is, like Jay said, 5 over 3 there.
Oh, 5 over 2, right? Because it's...
Oh, sorry,
Okay.
A, yeah, 5 over 2.
When I multiplied that out, I got 8.75 times 10 to the negative.
Okay, very good. Excellent. So, Camille, here we go. Another reaction. 3A plus 2B equals C. We measured the rate of B. How is the rate of C going to relate to the rate of B?
It's going to be doubled.
Doubled? So, is that what you said? So we measured the rate of B. How does...
It's going to lose 2.
Lose 2?
Is it like the top one?
It is. It is. Similar to the top one.
So would it be 5?
Well, let's see. Well, it's not that much like the top one. But it's not exactly the same reaction, right? We have a slightly different scenario going on here. But we've said that we measured the rate of B. Let's say B disappears at some value, 1 molar per second maybe. That's the rate of B's disappearance. So how is that going to relate to the rate of C? And, because C is a product, C has to be appearing. So how is the rate of C going to be related to the rate of B's disappearance?
Is it going to be slower?
Slower?
Yeah.
So the stoichiometry here is we need moles of B compared to moles of C, right? The molar concentration in stoichiometry. And because B is 2 to what?
1.
To 1, then the rate of appearance of C will be half as much. Very good. So the rate of C will be half that of the rate of B. All right. So one more here. We'll take Sarah. What do you think here? Here's a reaction. The rate of the reaction of carbon monoxide is measured to be 2 molar per second. What would the rate of the reaction of oxygen gas be?
One second. So we have, this is, so I think it would be the same.
The same? So
Yes.
here's carbon monoxide, right?
Yeah.
And we're looking at the rate at which oxygen gas disappears. Right?
Yes.
So if we draw a little picture for ourselves, carbon monoxide, right, reacting with oxygen gas. I need 2 carbon monoxides, though, correct, to react with 1 oxygen gas to form a carbon dioxide, right? And it's actually going to form 2 carbon dioxides, right? So for this process to occur once, every time it occurs, I have to consume 2 of these and 1 of those.
Right.
Do you agree with that?
Yes.
So if we know that the rate of disappearance of this stuff, if it's disappearing at 2 molar per second, then its concentration is only going to disappear at 1 molar per second. Right? Because only 1 is needed for every 2 of these. Can you see that?
Yeah.
So what would be the answer up there?
So it would be C, I think.
That's right. Very good. So it's the rate is half as fast, right, at which the oxygen is disappearing. Good. All right. Where are we at? Let's stop there.